So let me talk about homomorphism of waveguides and transmission lines. Waveguide problems are very complicated and we don't like that, but we can actually find a one-to-one mapping between waveguide problems and transmission line problems. And transmission line problems are very simple and we know how to solve them. You can even solve them with Smith charts. And it turns out that you can see this homomorphism in the rectangular waveguide, for instance, or it can be a circular waveguide. The TE case can be mapped to the transmission line problem, and then the TM case can also be mapped to the transmission line problem. And let's see how we can see this. So let's look at the TE case for a general hollow waveguide. Okay, this is to be hollow waveguide. And in this case, EZ is equal to 0. And we know that curl of H would be equal to J omega E, or I again forget the epsilon. This would have to be the case. And I'm going to do some kind of detailed analysis saying that my del operator can be broken up into a transverse part plus a longitudinal part, where del S is X partial X plus Y partial Y. Del Z is the longitudinal part, which is just partial Z. And then if I go through the analysis and expand this term, the left-hand side would be this term crossing with H, which can also be broken up into a longitudinal part plus the transverse part. And use the distributive law for a cross product, I would obtain 4 terms on the right-hand side. The 4 terms are, the first term is this term, and then the next term is curl Z cross HS. And then I have the third term, which is curl S cross HZ. And then the other term is curl Z cross HZ. Curl Z cross HZ equal to 0. Okay. Then I can see that if I were to just pick out the transverse component, only these 2 terms would have transverse component. This is purely pointing in the Z direction because it's transverse crossing with transverse. Transverse crossing with transverse give me a Z component. So I can immediately see that the transverse component has to come from the last 2 terms, because Z cross with S give me a transverse component. S crossing with Z give me a transverse component. And hence, I can write Ampere's law in this manner, saying that curl Z cross HS plus curl S cross HZ must be equal to J omega epsilon ES. Okay, I'm just picking up the transverse component of that thing. And I like to make this equation look very much like the transmission line equation or the telegrapher's equation. And I like to remove or eliminate HZ and substitute HZ with another expression so that I can get this equation to look as much like the telegrapher's equations as possible. So I look at the other equation, which is Faraday's law, to see if we can find a way to substitute for HZ. And if I look at Faraday's law, I can write in this manner. And again, I would do the decomposition of the del operator. I would do the decomposition of the electric field. On the left-hand side, I would have del S cross EZ, ES, plus del Z cross ES, plus del S cross EZ. And again, I only have 3 terms on the left-hand side. And on the right-hand side, I would have HS plus HZ. Okay. My goal is to eliminate HZ. So I want to find an equation from HZ from Faraday's law to eliminate HZ. I find that HZ is here. Okay. And it must be equal to this term because the other terms are transverse. So if I were to just equate HZ, I find that HZ has to satisfy this equation. Curl S cross ES must be equal to minus J omega mu HZ. So I'm almost there. I find a way of eliminating HZ. And I go back to this equation again, okay, and plug it HZ in there, and I get an equation that looks something like this now. Curl Z cross HS plus curl S cross 1 over minus J omega. I take this J omega mu to the other side and then put curl S cross ES there. And then I must have my right hand side again. So the Ampere's law or Faraday's law, no, is it? Yeah, this is Ampere's law. Ampere's law becomes something like this, but I need to simplify this in order to make this equation look like the telegrapher's equation. So I can again have something that looks like this. Here you can see that the second term is just that. And I can use the back of the cat formula and say that this is, you should know the back of the cat formula like the back of your hands now. Okay. And I know that divergence of E equal to 0 in this waveguide, but I'm looking for TE modes. Remember, I'm looking for TE mode. So EZ equal to 0. So EZ equal to 0, then this equation radially reduces to the transverse divergence of ES must be 0. And hence, this must be true. And double curl operator gets simplified. It just becomes a Laplacian. Okay, it just becomes a Laplacian. ES is what it becomes. But I'm going to assume that the modes or the fields inside the waveguides are traveling waves. If they're traveling waves, it means that I can actually say that, let me not get there first. Okay, I have this equations or this term that I need to simplify. And let's see how I can simplify that. I first noticed that the total field must satisfy this Helmholtz equation in a source-free medium. When the medium is source-free, this must be true, but then E has only ES. Okay, so I can know that this is true, and then I can write my total Laplacian as the transverse Laplacian plus the longitudinal component. And this must be true. And partial square, partial Z square for waveguide modes of this form. If you have such a kind of mode inside the waveguide, partial square, partial Z square becomes minus beta Z square. And hence this becomes now transverse Laplacian plus beta S square, which is the reduced wave equation that we had previously, where beta S square is beta square minus beta Z square, some sort of a reduced wave number. So this term, make the long story short, is that this term can be simplified to that, and this transverse Laplacian is just a negative of this thing. Okay, so if you do that, then the equation above can be simplified, and I would have curl of H. Okay, I'm going to simplify this term now. This term is going to be simplified down to something very simple. With the transverse Laplacian, this term goes to 0. And the equation that I finally would have is that the left-hand side was this. Okay, this is the first term. And then I will put this term to the right-hand side and then replace it with this simplification. And it will have this term on the right-hand side still. I will still have this term on the right-hand side. When I move this term to the right-hand side with all these ensuing simplifications, it becomes something like 1 over J omega mu beta S square ES square. Okay, I'm essentially using the last equation to make this simplification. And if that happens, then I can rewrite this equation in such a way that this is equal to, let me use the next slide to clarify things. Okay. So if I write this carefully, then I will have curl Z cross HS equal to the right-hand side. Right-hand side can be written as J omega epsilon. I'm going to group these two terms together. Okay, I'm going to group these two terms together. ES, group them together and use the definition of what the beta square is. And then if you do that, then this would be just ES. And then if you look at what this is actually J omega epsilon beta Z square over beta square ES. Okay, because if you take this over there, it becomes beta square minus beta S square, and that becomes beta Z square. So this looks strikingly like the transmission line equation now, or the telegrapher's equation. And I can actually write this out in some other ways. And if I write the left-hand side, I would just have partial Z, Z cross HS equals to, and I can use the cosine angle to define my beta Z, and the right-hand side can be written as cosine squared theta E sub S. Okay. And then I need another equation because this is not everything of the telegrapher's equation. The other equation I get from these other equations that I have. Okay, I can look at Faraday's law again, which I use a little bit of it. If I use a little bit of it here, Faraday's law. Okay, I use that to get Hz, but I can equate the transverse component. Okay, assuming that Ez equal to 0. If Ez equal to 0, if I equate the transverse component, I end up with this equation, which is partial Z, Z cross ES equals to minus J omega mu HS. And voila, we have something that looks like the telegrapher's equation. Because it's a partial Z on the left-hand side, it has a constant term on the right-hand side. And you can liken this to what you have learned in telegraphy theory. And if you do the map that ES maps to V, and then you do the map that Z cross HS maps to the current I, and then mu goes to the inductor, and then epsilon square cosine square theta, not epsilon square, epsilon cosine theta maps to the line capacitor. Then you have the telegrapher's equation. Okay, this will be the telegrapher's equation. And then you can define a characteristic impedance, which is this. And for this particular case, you'll find that it becomes just omega mu over beta Z. Okay, beta Z is the beta Z of the rectangular waveguide. Okay, and then you can repeat for TM case. What the lesson to be learned, the moral of the story is that given the complicated waveguide problem with a lot of field components, you can actually map the waveguide problem into a simplified transmission line problem, which means that if I have a complicated problem such as this one over here, I can map all the waves that are propagating inside this waveguide into a transmission line problem, okay, and solve it using Smith chart. And the trick is that when you have junctions that are not so nice as this one, you have something very tricky. Something that happens very trickily is the concept of mode conversion. You need more than one mode to match the boundary condition at the junctions of the waveguide, which means that if you have a pure TE10 mode coming in, it will be converted into many modes or multitudes of modes at the waveguide junction. And matching of this problem is a lot more difficult than just a simple transmission line problem. And usually in microwave engineering, we find approximate methods to solve this problem. Okay, I'll stop here since I have run over time. Are there any questions?